So far, we have learned how to evaluate a formula relative to one single valuations, and we have also learned how to evaluate a formula relative to all valuations. The next task, the task for this video, is to explore how we can evaluate an argument, namely a set of formulas where some formulas constitute the premises of the argument and one formula constitutes the conclusion of the argument. So the question is, how can we determine whether the argument is valid or not? And in particular, we will be focused on deductively valid arguments. So this is the topic of this video. So let's define what a deductively valid argument is. In the language of propositional logic and using the terminology and the machinery that we have developed so far, we can define a deductively valid argument as an argument in which whenever all valuations that make true the premises, the conclusion is also made true by these valuations. This definition of deductively valid argument corresponds to a more common or informal definition, according to which an argument is deductively valid whenever the premises are true, the conclusion is always true. So there are no situations, there is no possibility in which the premises are true and the conclusion is false. We call the argument pattern modus ponens. Here is one example. If you take the medication, then you will get better. You are taking the medication, therefore, conclusion, you will get better. This argument pattern can be formalized in the following way: if P, then Q, P, therefore Q. The task now is to determine whether this argument pattern, modus ponens, is valid or not. In order to determine whether modus ponens is valid or not, we can use a truth table, an expanded truth table that encompasses both premises and conclusion. We can construct the truth table in the following way. We list first the premises, so P and P implies Q are the two premises, and then the conclusion Q, and we separate the premises and the conclusion in some way that is visibly apparent, for example, by this vertical double line. And then we assign all possible valuations to P and Q. Since there are two atomic propositions here, there are a total of 4 possible valuations. So we can assign one to both P and Q, and here you see that P is repeated again. We can assign 1 to P but 0 to Q. Another possibility is that we assign 0 to P but 1 to Q, or we can assign 0 to both P and Q. Once we have assigned all the possible valuation, we need to consider the truth values of the different formulas that consist, that make up premises and conclusion. Now, one formula that make up the premises is P. Well, this is just an atomic formula, so we have its truth values already listed here, so we don't need to do anything extra. Another formula that plays the role of the premises, P implies Q. Now here we need to do a little bit of more work because we need to determine the truth value of the implication. Now, if the antecedent P is true and the consequent Q is true, then the implication has truth value 1. If the antecedent P is true, but the consequent Q has truth value 0, then we know that the implication has truth value 0. This follows from the truth table of the implication. If the antecedent P has truth value 0, then, and this is the case in the last two cases here, then we know that by definition the implication will have truth value 1, regardless of the truth value of the consequent Q. So now we have determined the truth value of both the two premises. What we want to know now is whether the argument that is modus ponens, the argument pattern modus ponens, is valid. And remember that valid means that whenever the premises are true, the conclusion is always true. So we need to consider only the cases in which both premises are true. The case in which both premises are true are the case, this first case here, because P is true, and then P implies Q is also true. All the other cases we don't need to consider because in some cases P is true, but the P implies Q is not true, or in some cases P is false and P implies Q is true. So the only case that we need to consider is the first one, in which both premises are true. And we see that in this case the conclusion Q is also true. And so our definition of deductively valid argument is satisfied. Whenever the premises are true, the conclusion is also true. So modus ponens is deductively valid. And I want to emphasize one more time that we only need to consider the first row of the table because that's the row where both premises are true. Now that we have established that modus ponens is deductively valid, we can also write this in the following form: P, P implies Q, and we use again the symbol for with the vertical bar and the two horizontal bar, Q. So that simply means that the argument pattern P from P implies Q towards the conclusion Q is deductively valid. Consider another form of argument. We saw earlier modus tollens as opposed to modus ponens. An example of modus tollens is this argument: if you take the medication, then you will get better. You are not getting better. Conclusion: you're not taking the medication. If we were to symbolize this, we can write it: if P, then Q, not Q, therefore not P. Or even more succinctly, P implies Q, not Q, therefore not P. This is modus tollens, and we want to know whether modus tollens is a deductively valid form of argument or not. Again, what we need to do is to use an extended truth table where we list both premises and conclusions, and we assign truth value to all the propositions involved. So the two premises that we are considering here are not Q, and then P implies Q, and then the conclusion is not P. The truth value, since we have two atomic propositions, we have in total 4 possible valuations. So we can assign one to both P and Q. We can assign 1 to P and 0 to Q. we can assign 0 to P and 1 to Q, or we can assign 0 to P and 0 to Q. Since we have done that, whenever we assign 1 to P and Q, we need to assign 0 to not Q and 0 to not P. In the second line, we assign 1 to P, and therefore we need to assign 0 to not P, but we assign 0 to Q, and therefore we need to assign 1 to not Q. In the third line, we assign 0 to P, and again, we need to assign 1 to not P, but we are assigning 1 to Q, and therefore we need to assign 0 to not Q. Finally, in the last row, we assign 0 to both P and Q, and therefore we need to assign 1 to both not Q and not P. There is one more thing that we need to do. We need to determine the truth value of P implies Q, given all the possibilities. And the truth value of the implication is true whenever both antecedent and consequent are true. So in the first row, we assign 1 to the implication. Whenever the antecedent is true but the consequent is false, the truth value of the implication is 0. So here we are assigning 0. And then whenever the antecedent P is false, as in these two cases, we can simply assign 1 to the implication regardless of the truth value of the consequent. So we have assigned all the truth values that we need to assign to the two premises and to the conclusions as well. And now we need to check whether modus tollens is valid. And remember that the definition of valid argument is that whenever the premises are true, the conclusion is always true. So once again, we only need to consider the cases in which both premises are true. And in this table, we see that there is only one row where both premises are true, namely the last row. Here, not Q is true, as assigned valued 1, and P implies Q is also true, so has been assigned truth value 1. And we see that in this case, also the conclusion not P is true, because it's been assigned truth value 1. So we can conclude once again that modus tollens is a valid form of argument. And I want to emphasize one more time that we only need to consider the case in which both premises are true. So in this case, we only need to consider the last row. And once we do that, we can conclude that modus tollens is a valid form of reasoning, and we can write that it is valid in the following way. We can write not Q, comma, P implies Q, and then the usual symbol, and then not P. This tells us that modus tollens is a valid form of argument.